Imagine you're drifting backward away from Earth, up through the atmosphere, past the Moon, beyond Mars and Jupiter, out past the orbit of distant Neptune. Keep going. Past the edge of our solar system, past the realm where the sun's influence fades into the dark. You're traveling outward now, watching our sun shrink to just another point of light among billions. But look back the other way. Look toward the center of everything we know. About 26,000 light-years away, hidden behind vast clouds of dust and gas, something waits, something massive beyond comprehension. Something that has been there since before our sun was born, quietly shaping the architecture of our entire galaxy with its gravity alone. At the heart of the Milky Way, in a region so dense with stars they blur together like grains of sand on a beach, there sits a monster. Not a monster of teeth and claws, but one of pure gravitational force, a supermassive black hole, about 4.3 million times the mass of our Sun, compressed into a space smaller than the orbit of Mercury. It has a name that sounds like a whisper, Sagittarius A star. We call it Sagittarius A star. And for decades, we could only infer its presence by watching the things that dance around it. This is a story about patient watching, about stars that move so fast they test the limits of physics itself, about the quiet persistence of gravity and light, and about the remarkable human effort to see something that, by its very nature, cannot be seen. Tonight, we're going to journey to the center of our galaxy. We're going to meet the monster that lives there, and we're going to discover that even in the most extreme places in the universe, there is pattern, there is beauty, and there is something approaching peace. If you find these quiet explorations soothing, if you enjoy these journeys to the edges of what we know, please consider liking this video or subscribing to the channel. It helps others find their way here too, one curious soul at a time. But for now, just settle in. Let your breathing slow. Let the concerns of the day drift away like stars passing in the night. And let's begin our descent into the hidden heart of everything we call home. The hidden heart. For most of human history, the center of the Milky Way was invisible to us. Not because it wasn't there, obviously, but because we couldn't see it. Between us and that distant center lies an enormous barrier of dust and gas, clouds of material so thick that visible light simply cannot penetrate. When you look up at the night sky and trace the band of the Milky Way across the darkness, you're seeing the disk of our galaxy edge on, spread out like a river of light, but right where it's brightest, right where it's densest, there's a dark patch. A region where the stars seem to disappear, where the light fades into shadow. The astronomers of centuries past called these patches dark nebulae, thinking they were voids, empty spaces where no stars lived. They were wrong, of course. Those dark regions aren't empty at all. They're full of dust, thick veils of microscopic particles, grains of silicate and carbon, and ice smaller than the width of a human hair, floating in vast clouds between the stars. These particles absorb blue and ultraviolet light completely, and scatter red light, dimming and reddening the light from any star unlucky enough to lie behind them. And the thickest veil of all hangs between us and the galactic center, blocking our view of the very heart of our cosmic home. It's like trying to see through fog so thick you can't see your hand in front of your face, except the fog is thousands of light years deep and made of cosmic dust. For thousands of years, we didn't even know there was a center to find. The ancient Greeks thought the Earth sat motionless at the middle of everything, with the stars wheeling around us in perfect crystalline spheres, eternal and unchanging. Later, Copernicus moved the sun to the center, but still the stars seemed fixed, points of light painted on a distant sphere that rotated once a day. It wasn't until the 20th century that we began to understand the true scale of things, that we realized the sun was just one star among hundreds of billions, all of them orbiting a common center, all of them part of a vast disk that slowly, majestically, turns through space over the course of hundreds of millions of years. But where is that center? What sits at the pivot point around which an entire galaxy wheels? The first clue came not from visible light, but from radio waves. In the early 1930s, a young engineer named Carl Jansky was working for Bell Telephone Laboratories, trying to track down sources of static that interfered with radio communications. He built a large rotating antenna in a field in New Jersey, and he began to catalogue the hisses and crackles that came from different parts of the sky. Most of them were from thunderstorms, as expected. But there was one source of static that moved with the stars. It appeared at the same point in the sky each day, rising and setting with the regular rhythm of the celestial sphere. Jansky traced this mysterious radio source to the constellation Sagittarius, right in the direction of what we now know is the center of the Milky Way. He couldn't see what was making the radio waves, couldn't identify a particular star or object, but he had found something. A bright spot in a part of the electromagnetic spectrum that dust doesn't block radio waves, with their long wavelengths can slip right through the cosmic fog that stops visible light cold. For decades after Jansky's discovery, astronomers listened to the radio sky, refining their instruments, sharpening their resolution. In 1974, two astronomers named Bruce Ballack and Robert Brown were using radio telescopes to map the galactic center in finer and finer detail, and they found something extraordinary. Right at the very heart of the region, there was a compact, incredibly bright radio source. It was small, far smaller than anything else they'd seen, and it was brilliant in radio light. They called it Sagittarius A, and they marked its special nature with an asterisk, the same symbol physicists use to denote an excited state of an atom Sagittarius A star. The star that wouldn't be seen but could be heard if you had the right ears. But what was it? A dense cluster of stars, perhaps, packed so tightly together they appeared as a single point? An unusual kind of stellar remnant? Or something else entirely, something whose existence was still mostly theoretical? The answer would come from watching. Not listening with radio telescopes, though that continued, but watching in infrared light, which could also pierce the veil of dust. Watching the stars that lived near Sagittarius A star. Watching how they moved. And what the astronomers saw when they began to track individual stars near the galactic center was astonishing. The stars were moving fast. Not the gentle drift of stars across the galaxy, taking millions of years to complete their orbits, but genuinely fast. Some of these stars, the ones closest to Sagittarius A star, were whipping around in elliptical paths at speeds that seemed impossible, thousands of kilometers per second, percents of the speed of light. And they were orbiting something invisible, something that had to be incredibly massive to whip stars around like that, and incredibly compact to fit inside the volume of their orbits. Throughout the 1990s and into the early 2000s, two teams of astronomers, one led by Reinhard Genzel in Germany and one led by Andrea Ghez in the United States, painstakingly tracked these stars year after year, observation after observation, watching the tiny points of light creep across the dark, measuring their positions to extraordinary precision. They gave the stars simple names: S1, S2, S14, numbers in a catalogue of objects that were about to rewrite our understanding of the galactic center. The dust made it hard. The sheer distance made it harder. 26,000 light-years is an almost incomprehensible span. Light itself, traveling at 300,000 kilometers per second, takes 26,000 years to make the journey from there to here. We're seeing these stars not as they are now, but as they were when the last ice age on Earth was just ending, when mammoths still walked the tundra and humans were learning to plant the first crops. But watch long enough, measure carefully enough, and patterns emerge. The stars trace paths through space, elegant ellipses that swing in close to the dark center and then arc out again into the relative safety of the distance. And from those paths, from the speed of the stars and the shape of their orbits, you can calculate what must be sitting at the focus of those ellipses. You can weigh the invisible. What sits at the center of the Milky Way is a black hole. Not a modest stellar mass black hole, the corpse of a single massive star, but a supermassive black hole, the kind that lurks at the hearts of galaxies, the kind that contains the mass of millions of suns compressed into a volume smaller than our solar system. The watching revealed it. The patient, careful decades-long watching of stars dancing around an invisible partner. And as the evidence mounted, as the orbits became clearer and the calculations more certain, there could be no doubt. Sagittarius A star is a supermassive black hole. The monster at the center of our galaxy. The massive anchor around which everything we see in the night sky ultimately revolves. The dance of stars. If you want to understand something invisible, watch what dances around it. Watch long enough, carefully enough, and the invisible becomes undeniable. This is what astronomers did with Sagittarius A star. They watched the stars, and the stars told them everything. Near the galactic center, in a region dense with stellar light, there's a cluster of stars that have come to be called the S stars. They're catalogued simply S1, S2, S4, and so on, numbered roughly in the order they were identified and studied. But these simple designations hide something extraordinary. These stars are living in one of the most extreme environments in the entire galaxy. They orbit within light weeks of a supermassive black hole, experiencing gravitational forces so intense that the very fabric of space-time bends around them. One star in particular has become famous among astronomers. Its name is S2, though some call it S0-2, depending on which research team's catalogue you're using. Either way, it's the same remarkable object. A star about 15 times the mass of our Sun, burning bright and hot, a blue giant that would be spectacular to see if we could visit it up close. Its surface temperature exceeds 30,000 degrees, making it shine with an intense blue-white light that cuts through even the dusty veil of the galactic center. It's young, only a few million years old, still in the prime of its stellar life. But what makes S2 truly extraordinary isn't its size or its brightness, it's where it lives and how it moves. To understand what makes S2's orbit so remarkable, you need to grasp the scale of what's happening. This isn't like watching the planets move across the sky over months and years. This is watching a star, a massive ball of plasma bigger than our entire inner solar system, whip around an invisible point at speeds that make jet airplanes look like they're standing still. The astronomers who first began tracking S2 in the mid-1990s didn't know exactly what they were seeing at first. Just a bright point of infrared light in a crowded field, moving detectably year to year. But as the observations accumulated, as they built up a baseline of measurements spanning first years, then a decade, then longer, the orbit became clear. S2 orbits Sagittarius A star in an ellipse that takes 16.05 years to complete, just over 16 years. 16 years. Think about that for a moment. Our Sun takes about 230 million years to complete one orbit around the galactic center. Neptune takes 165 years to orbit our Sun. But S2, orbiting something with a mass of roughly 4.3 million suns, completes its circuit in a human lifetime's fraction. Imagine what that orbit looks like. For most of those 16 years, S2 is relatively far from the black hole, several thousand astronomical units away, traveling at speeds that, while fast by stellar standards, seem almost sedate. A few hundred kilometers per second, perhaps, which is normal for stars near the galactic center. The star moves through its orbit like a celestial clock, marking time with its position against the background of more distant stars. Astronomers photograph it, measure its coordinates, plot its path across the sky. The motion is smooth, predictable, following the gentle curve of an ellipse. But as it swings around toward its closest approach, something remarkable happens. The star begins to fall. Not fall into the black hole, not yet, but fall toward it, accelerating under the inexorable pull of 4 million solar masses compressed into a space no larger than Mercury's orbit around the Sun. This isn't a gentle descent. This is gravitational acceleration on a scale that defies easy comprehension. Every day that passes, S2 moves faster. Every hour, its velocity climbs. The black hole's gravity reaches out across the light weeks of distance and pulls relentlessly, impossibly strong. Think about the forces involved. S2 is 15 times the mass of our Sun, something like 2 times 10 to the 31st kilograms, a number with 31 digits, and it's being accelerated continuously by gravity alone. No rocket engines, no external force besides the curvature of space-time itself, and it accelerates smoothly, gaining speed, falling inward year after year as perihelion approaches. Faster and faster, S2 moves thousands of kilometers per second, 5,000, 7,000, at its absolute closest approach at the moment of perihelion when it swoops past the black hole at a distance of just 120 astronomical units. About 17 light-hours away, S2 is traveling at nearly 3% of the speed of light. 3%. That's about 9,000 kilometers per second, faster than anything you've probably imagined outside of particle accelerators or science fiction. At that speed, if you could somehow stand on S2's surface and look out, you would see strange things. The stars ahead of you would appear blue-shifted, their light compressed by your motion toward them. The stars behind would redshift into dimness, and if you looked toward Sagittarius, a star, you wouldn't see a black hole, not exactly. You'd see a region where stars disappeared, where the background light bent and curved around a darkness that wasn't quite dark, because gravitational lensing would bend the light from stars behind the black hole around it, creating a strange glowing ring in the void. But S2 doesn't crash into the black hole. It survives. At 120 astronomical units, it's still safely outside the event horizon, still in a realm where escape is possible. The black hole's event horizon, the point of no return, is much closer, just 12 million kilometers across, or about 0.08 astronomical units. S2 passes about 1,500 times farther out than that. Which sounds safe, but in cosmic terms it's a hairbreadth. It's like skimming past the surface of the Sun at a distance of a few hundred solar radii, close enough to feel the monster's grip, but far enough to break free. And break free, it does. After that screaming perihelion passage, S2 climbs back out of the gravity well, slowing gradually as the black hole's pull fights against its outward motion. It arcs out into the relative calm of the outer regions, where it will spend the next 8 years or so before beginning its inward fall again. The orbit is eternal, a cosmic clockwork, a dance that has been going on for far longer than humans have existed and will continue long after we're gone. But S2 isn't alone in this dance. There are dozens of other S-stars, each with its own orbit, its own speed, its own relationship with the central monster. Some orbit at greater distances, taking decades or centuries to complete their circuits. A star called S4714 appears to hold the current record for the closest approach, though measurements of its orbit carry substantial uncertainty. Based on observations, its orbit may bring it within about 12 to 13 astronomical units of Sagittarius A star, roughly as close to the black hole as Saturn is to our Sun. At that distance, at what could be its perihelion, S4714 might be traveling at roughly 8% of the speed of light, perhaps 30,000 kilometers per second. The violence of such a passage would be almost unimaginable if the measurements are confirmed. These stars are young, or at least young by stellar standards. Most of them are only a few million years old, which raises an intriguing puzzle. How did they form so close to the black hole? The tidal forces near Sagittarius. A star should tear apart the clouds of gas and dust that normally collapse to form stars. The environment appears too hostile, too violent for star formation to occur. Yet here these stars are, thriving in what seems like the most extreme stellar nursery we know of. The current thinking among astronomers offers a few possibilities. They might have formed farther out and then migrated inward, captured by the black hole's gravity over time. Or perhaps they formed in a particularly dense disk of material that briefly existed close to the black hole, a disk massive enough to resist the tidal shearing. Some researchers have even proposed that they could be the products of stellar collisions or mergers that occurred in the crowded environment near the galactic center. However they originated, they're there now, and they're providing us with an extraordinary natural laboratory for testing the predictions of general relativity in an extreme gravitational environment. Because here's the thing about S2 and the other close-orbiting stars. Their movements aren't quite what Newton would have predicted. According to Newtonian gravity, when an object orbits another in an ellipse, that ellipse should remain stationary in space. The orbit is closed, repeating exactly with each circuit. But according to Einstein's general theory of relativity, orbits in strong gravitational fields should precess. The ellipse itself should rotate slowly, creating a rosette pattern over multiple orbits. The closest point of the orbit, the perihelion, should shift forward with each pass. This effect, called Schwarzschild precession, was first observed in the orbit of Mercury around the Sun. Mercury's perihelion precesses by about 43 arc-seconds per century, a tiny amount, but enough to be measured, and enough to provide one of the first great confirmations of Einstein's theory in 1915. But Mercury's precession is minuscule compared to what happens at the galactic center. S2's orbit precesses by about 12 arc-minutes per complete orbit. 12 arc-minutes, which is 1/5 of a degree. That might not sound like much, but it's enormous compared to Mercury. It means that over the course of several orbits, S2 doesn't trace the same path through space. Instead, it creates a rosette, like a spirograph drawing, its ellipse slowly rotating around Sagittarius A star. And here's the beautiful thing. The amount of precession matches Einstein's predictions exactly. When Reinhard Genzel's team published their measurement of S2's Schwarzschild precession in 2020, they found that the observed precession agreed with general relativity to well within the measurement uncertainties. There was no room for alternative theories of gravity. No sign that Einstein's century-old equations were breaking down, even in this extreme regime. The orbits of stars around Sagittarius A star dance exactly as Einstein said they would. For this work, for the decades of patient observation that revealed the supermassive black hole at the center of our galaxy and tested general relativity in its most extreme environment, Reinhard Genzel and Andrea Ghez were awarded the 2020 Nobel Prize in Physics. They shared it with Roger Penrose, who proved mathematically that black holes are a natural prediction of Einstein's theory. 3 people honored for showing us the invisible monster and confirming that the universe, even at its most extreme, follows the beautiful mathematical patterns that Einstein glimpsed. The stars still dance. Right now, as you listen to this, S2 is somewhere along its orbit, moving at thousands of kilometers per second, carving its rosette around the invisible center. Other S-stars trace their own patterns, each one a testament to the gravitational architecture of the galactic core. And astronomers are still watching, still measuring, still learning. Because every orbit, every perihelion passage, every measurement of a star's position adds another data point to our understanding. The dance continues, and we are privileged to watch. 4 million suns in darkness. How much does a monster weigh? If that monster is a black hole, the answer is everything. Mass is all that matters. A black hole is mass without material, gravity without substance, curvature without content. It's what's left when matter becomes so dense that it disappears into its own gravity, leaving behind only the warping of space-time itself. Sagittarius A weighs in at about 4.3 million times the mass of our Sun. Let's sit with that number for a moment. Our Sun is already almost incomprehensibly massive. It contains 99.8% of all the mass in our entire solar system. Jupiter, Saturn, all the other planets, all the asteroids and comets and moons and dust, all of it together makes up less than 0.2% of the solar system's mass. The Sun is vast beyond everyday experience, a sphere of plasma so large you could fit over 1 million Earths inside it. Now multiply that mass by 4,300,000. That's Sagittarius A star. That's what sits at the center of our galaxy, warping space-time around itself so severely that not even light can escape if it gets too close. But here's what's strange, almost paradoxical. Despite that enormous mass, Sagittarius A star is actually quite small. Not small by human standards, obviously, but small compared to the scale of the galaxy, small even compared to some of the structures in our own solar system. The event horizon of Sagittarius A star, the spherical boundary beyond which nothing can escape, has a radius of about 12 million kilometers. That's the Schwarzschild radius, named after Karl Schwarzschild, who derived the first exact solution to Einstein's equations that described a non-rotating black hole. 12 million kilometers might sound like a lot, and it is. But consider, the Earth orbits the Sun at a distance of about 150 million kilometers Mercury. The closest planet to the Sun orbits at about 58 million kilometers at its average distance. The event horizon of Sagittarius A star is smaller than Mercury's orbit, much smaller. If you could somehow place Sagittarius A where our Sun is, it wouldn't even fill the orbit of Mercury. The black hole would sit there in the center, a sphere of absolute darkness just 12 million kilometers across, and Mercury would sail past it safely, never crossing that fatal boundary. Of course, Mercury's orbit would be drastically altered by the change in mass, but geometrically, spatially, it would fit. This is the nature of supermassive black holes. They're called supermassive because of their mass, not their size. The event horizon scales with mass growing larger as you add more material, but the density doesn't have to be extreme. In fact, the average density inside the event horizon of a supermassive black hole can be surprisingly low. For Sagittarius A, if you calculated the average density by dividing the mass by the volume inside the event horizon, you'd get something on the order of the density of water. Not the incomprehensible density of a neutron star or a stellar mass black hole, but something almost mundane. Of course, that's just an average, and it's not really physically meaningful because there's no material inside the black hole distributed at that density. All the mass is concentrated at the singularity at the very center, a point of infinite density where the known laws of physics break down. But it's a useful thought experiment, a reminder that supermassive black holes are supermassive because they've accumulated so much matter, not because they've compressed it to impossible densities. And Sagittarius A sits 26,000 light-years away from us. That's the distance from here From Earth, from our solar system at the edge of one of the galaxy's spiral arms, to the gravitational center around which we orbit 26,000 light-years. In more familiar units, that's about 153 quadrillion miles, about 250 quintillion kilometers, numbers so large they cease to have meaning in human terms. Light from Sagittarius, a star, or rather, light from the hot gas swirling around it, takes 26,000 years to reach us. When that light began its journey, humans on Earth were still living in small bands of hunter-gatherers. Agriculture hadn't been invented yet. The pyramids were more than 20,000 years in the future. Entire civilizations would rise and fall, entire epochs of human history would unfold before that light completed its journey through the galaxy to reach a telescope on a mountaintop on a small blue planet at the edge of the disk. And yet, of all the supermassive black holes in the universe, Sagittarius A star is the closest to us. It's our home galaxy's heart, our cosmic center. Every other supermassive black hole sits in a different galaxy, tens of millions or hundreds of millions or even billions of light-years away. The next closest, the supermassive black hole at the center of the Andromeda galaxy, is about 2.5 million light-years distant, 100 times farther than Sagittarius A star. This proximity, this relative nearness, is why we can study Sagittarius A star in such detail. It's why we can track individual stars in their orbits around it. It's why we can measure the black hole's mass to such precision, why we can test general relativity in its gravitational field, why we can even, as we'll see, take an image of the black hole's shadow. Distance is the enemy of astronomy, the fog that obscures detail, and Sagittarius, A star is close enough, just barely, that we can see through that fog and glimpse the monster itself. 4 million suns compressed into a sphere 12 million kilometers across, sitting at the center of our galaxy, warping space-time around itself, pulling everything in its vicinity into orbit, bending the path of every photon that passes nearby. This is the anchor, the gravitational heart, the massive pivot point around which 200 billion stars, including our own, slowly wheel in the cosmic dark. This is Sagittarius, a star. This is our monster. And remarkably, for all its power, it's quite quiet. The quiet giant. Here's something that puzzled astronomers for years. Sagittarius. A star should be much brighter than it is. A supermassive black hole with 4 million solar masses, sitting at the center of a galaxy, surrounded by gas and dust and stars, should be feeding constantly. Material should be falling in, spiraling down into the black hole's gravity well, heating up as it falls, glowing brilliantly across the electromagnetic spectrum. We see this in other galaxies. We see active galactic nuclei, quasars, blazars, objects where the supermassive black hole at the center is consuming matter so voraciously that it outshines the entire rest of the galaxy. Billions of stars, dimmed to insignificance by the ferocious light of gas falling into a black hole. But Sagittarius A isn't like that. It's dim. Remarkably, surprisingly, almost mysteriously dim. When astronomers measure its luminosity, its total light output across all wavelengths, they find something less than 1/100% of what they'd expect for a black hole of its mass actively feeding. It's as if the monster is asleep, or at least drowsy, barely nibbling at the material that surrounds it. Why? What makes Sagittarius a star so quiet? The answer has to do with how black holes feed, and with the difference between galaxies that are actively forming stars and galaxies like ours that are relatively mature and stable. When a black hole feeds efficiently, when it becomes bright and active, it's because there's a lot of material in its vicinity that has angular momentum that's swirling around in an accretion disk. As that material spirals inward, friction and magnetic forces heat it to millions of degrees, hot enough to radiate intensely in X-rays and other high-energy wavelengths. The material moves inward through the disk, gradually losing its angular momentum, gradually getting closer to the event horizon, glowing all the while. But for this to work, you need a steady supply of material falling in. You need something to feed the accretion disk. In galaxies that are actively forming stars, in galaxies that are undergoing mergers with other galaxies, there's plenty of gas available. Vast clouds of molecular hydrogen flow toward the center, channeled by the gravitational structure of the galaxy, and they pile up in the central regions where the black hole can feed on them. The Milky Way doesn't have that anymore. We're a mature galaxy. We're still forming stars, yes, but slowly at a rate of just a few solar masses per year across the entire galaxy. We're not undergoing any major mergers with other galaxies, not right now. We've settled into a relatively stable configuration, and that means there's not a lot of dense gas flowing toward the galactic center. There's some, of course, from stellar winds and the occasional star that gets torn apart by tidal forces, but it's a trickle, not a flood. The accretion rate onto Sagittarius A star, the rate at which material actually crosses the event horizon and adds to the black hole's mass, is estimated to be something like 1/10,000th of a solar mass per year. That's nothing. That's barely a snack in cosmic terms. To put it in perspective, imagine trying to sustain an elephant by feeding it a single grain of rice per day. That's roughly the equivalent of what Sagittarius A star is getting relative to what it could potentially consume if there were more material available. And most of that small amount of infalling material doesn't even radiate efficiently. It falls in so quickly, and the accretion flow is so hot and tenuous that most of the energy generated by the infall gets carried inward with the gas, advected across the event horizon before it has a chance to radiate away. The physics here is subtle and fascinating. When gas falls into a black hole, it heats up due to compression and friction. Normally, that heat would radiate away as light, and that's what makes actively accreting black holes bright. But if the gas is falling too fast, or if the accretion flow is too diffuse, the cooling timescale becomes longer than the infall timescale. The gas doesn't have time to radiate before it falls in. This is called an advection-dominated accretion flow, and it's extraordinarily inefficient at producing light. The material heats up as it falls, yes, reaching temperatures of billions of degrees in the innermost regions, hot enough that the particles are moving at significant fractions of the speed of light. But instead of that heat radiating away and making the black hole bright, the heat just disappears into the black hole along with the material. It's like trying to warm a room with a fireplace when the chimney is wide open and all the heat escapes outside before it can heat the air. You get some warmth, a flicker of flame, but most of the energy just goes away, lost forever across the event horizon. So Sagittarius A star sits there, massive and powerful, and yet dim, almost invisible, except for the faint glow of the hot, thin gas immediately around it. It's a sleeping giant, a monster on a starvation diet. But it wasn't always this way. Evidence from structures called the Fermi bubbles suggests that Sagittarius A star had a much larger meal sometime in the relatively recent past. These enormous lobes of high-energy gas extend tens of thousands of light-years above and below the galactic plane, and based on their size and energy, astronomers think they were created by a major outburst from the galactic center. The timing is uncertain, but current estimates place this event somewhere between 5 and 9 million years ago. That outburst likely occurred when Sagittarius A star suddenly gained access to a substantial supply of gas, perhaps from a molecular cloud that wandered into the central regions, and it fed more intensely for what might have been a few 100,000 years. The energy released by that feeding created shockwaves that pushed gas outward, inflating the bubbles we observe today. Perhaps 100 solar masses or so, consumed over what could have been a few 100,000 years. That's one interpretation of the Fermi bubble's properties, though the exact amount remains uncertain. It sounds like a lot, and by the standards of Sagittarius A's current diet it is, but it's still modest compared to what active galactic nuclei consume. Those beasts can devour solar masses per year, thousands or even millions of times more than Sagittarius A star managed during its last big meal. Since then, it's been back to quiet. The black hole feeds on the stellar winds from nearby stars, on the occasional wisp of gas that happens to lose enough angular momentum to fall inward, on nothing much at all. And so it glows faintly, a radio source, a dim X-ray emitter, a patch of infrared light, but nothing that would stand out as special if we didn't know to look for it. Except for the flares. Every so often, on timescales of hours or days, Sagittarius A star brightens suddenly. These flares can be quite dramatic, increasing the X-ray and infrared output by factors of 10 or even 100 for a brief time. Astronomers think they're likely caused by magnetic processes in the accretion flow, similar to solar flares, but vastly more powerful. When magnetic field lines in the hot plasma near the black hole reconnect, the current models suggest they can suddenly accelerate particles to enormous energies, and those particles radiate intensely until they either escape or fall into the black hole. NASA's James Webb Space Telescope has been watching these flares recently, tracking them with unprecedented time resolution, observing how the brightness changes minute by minute. What they see is fascinating. There's a constant low-level flicker, a background variability driven by turbulence in the accretion flow. And then, superimposed on that, there are sharper, brighter events, the magnetic reconnection flares, that pulse and fade over the course of minutes to hours. It's like watching a small campfire, mostly steady, but occasionally spitting out sparks. The variability also tells us something important about the size of the emitting region. Light travel time matters. If you have a source that varies on a timescale of, say, 10 minutes, then the emitting region can't be larger than the distance light travels in 10 minutes, or about 180 million kilometers. Otherwise, different parts of the source would be out of sync, and you wouldn't see coherent variability. The fact that Sagittarius A star varies on timescales of minutes tells us that the hot glowing gas producing the emission is very close to the event horizon. Within a few Schwarzschild radii at most, we're seeing right down into the throat of the monster, watching the material in the last moments before it falls in. And despite all this, despite the flares and the hot plasma and the extreme environment, Sagittarius A star remains fundamentally quiet. It's a supermassive black hole in a state of near quiescence, sipping gently at the material around it, not gulping it down. It's nothing like M87, the supermassive black hole at the center of the giant elliptical galaxy Messier 87, which is actively feeding and producing a relativistic jet thousands of light years long. M87 star is a beast fully awake. Sagittarius A star is drowsing. But both, as we'll see, look remarkably similar when you manage to take their picture. Because despite their different feeding rates, despite the differences in their environments, they're both black holes. And black holes, Einstein tells us, are remarkably simple objects. They have mass, they might have spin, they might have electric charge, but beyond that, they're all the same. A black hole is a black hole is a black hole. And that similarity, that universality, makes them almost beautiful in their simplicity. The quiet giant sits at our galactic center, barely feeding, barely glowing, but still shaping everything around it with the inexorable pull of its gravity. And we, some 26,000 light-years away at the edge of the galactic disk, watch and measure and try to understand. Even quiet monsters are worth studying, especially quiet monsters. Capturing the shadow. How do you take a picture of something that doesn't emit light? Something that is, by definition, black? The answer is, you don't exactly. You take a picture of the light around it, the light that almost made it past, but didn't quite. You photograph the shadow. For years, the idea of directly imaging a black hole seemed impossible. Supermassive black holes are small, even the nearest ones, and they're very far away. The angular size of Sagittarius, a star as seen from Earth, is about 50 microarcseconds. To put that in perspective, that's like trying to see a tennis ball on the moon. It's like reading the date on a coin in Los Angeles from New York City. It's absurdly, impossibly small. No single telescope on Earth, no matter how large, can achieve that kind of resolution. The resolution of a telescope is limited by diffraction, by the wave nature of light itself. And to see something that small, you'd need a telescope aperture the size of the Earth. So that's what astronomers built. Not physically, of course, but effectively. They created a virtual telescope the size of the planet by using a technique called Very Long Baseline Interferometry, or VLBI. The idea is beautifully simple, even if the execution is extraordinarily complex. You take multiple radio telescopes scattered across the Earth, you point them all at the same target at the same time, and you carefully synchronize their observations using atomic clocks locked to GPS time standards. Then you take all the data from all the telescopes and combine it, using the differences in arrival times and phases of the radio waves at each telescope to reconstruct an image as if you had one giant telescope with an aperture equal to the distance between the outermost telescopes. The Event Horizon Telescope, or EHT, is a collaboration of radio observatories around the world that have been doing exactly this. In April 2017, they pointed 8 radio telescopes at Sagittarius A star, observing simultaneously at a wavelength of 1.3 millimeters. The telescopes were spread across the world, from Hawaii to Arizona to Chile to Spain to the South Pole. Together, they created a virtual telescope with a diameter roughly equal to that of Earth itself, achieving an angular resolution of about 25 microarcseconds, just barely enough to resolve the shadow of Sagittarius, a star. But getting the observations was only the beginning. The data had to be collected, physically transported from remote observatories because there was far too much of it to send over the internet. Something like 5 petabytes of data in total. The hard drives were shipped by airplane and truck to central processing facilities in the United States and Germany, where teams of researchers began the painstaking work of correlating and analyzing everything. And here they ran into a problem unique to Sagittarius A star. The black hole is small enough, and the accretion flow around it is hot enough that material orbits the black hole very quickly, completing a full orbit in just a few minutes. Think about that. Material at the innermost stable circular orbit, the closest you can orbit a black hole before you have to plunge in, goes around Sagittarius A star in something like 20 to 30 minutes. That means the appearance of the source changes on minute timescales. The bright spots in the accretion disk move, flare up, fade away, shift position, all while you're trying to observe them. It's like trying to take a long exposure photograph of someone who can't sit still, who's fidgeting and moving and changing expression continuously. Every image you capture is blurred by the motion, smeared out by the variability. For M87 star, which the Event Horizon Telescope had imaged in 2019, this wasn't as much of a problem. M87 star is so massive, over 1,000 times more massive than Sagittarius A star, that its innermost stable circular orbit is correspondingly larger and the orbital period is correspondingly longer. Material orbits M87 on timescales of days or weeks, not minutes. So you can average observations over hours or even days and still get a clear, stable image. But for Sagittarius A star, averaging doesn't work. Average over too long and you just get a blur. So the team had to develop entirely new imaging techniques, new algorithms that could handle rapid variability, that could essentially freeze the motion and extract the underlying structure from data that was changing while they watched. To deal with this, the team had to develop new imaging algorithms that could handle the rapid changes. They couldn't just average the data together the way they had for their earlier observations of M87 star, which is so large that its accretion disk changes much more slowly. Instead, they created thousands of different possible images, each one consistent with the data from a particular time period, and then looked for features that appeared consistently across many images. They essentially assembled the final image from fragments, from pieces that recurred even as the source varied. It took 5 years from the observations in April 2017 to the public release of the image in May 2022. 5 years of data processing, of algorithm development, of checking and rechecking, of making sure they weren't seeing artifacts or patterns that the algorithms had inserted, rather than real features of the source. 5 years of painstaking, careful work. And then finally they revealed what they'd found. The first image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. What did it look like? Almost exactly like M87 star, actually. A bright ring of glowing emission, orange-red in the false color image, surrounding a darker center. The ring isn't uniform. It has bright spots and dimmer regions, asymmetries caused by the motion of the hot gas and the effects of relativity as it whips around the black hole at a significant fraction of the speed of light, and at the center, the shadow. Not perfectly black, because there's some emission even in the center, but significantly darker than the ring. A circular patch about 50 microarc seconds across where the black hole sits. That shadow is the silhouette of the event horizon against the bright background of the accretion flow. It's actually about 2.6 times larger than the event horizon itself because of the way gravity bends light around the black hole. Photons that pass near the event horizon get deflected, bent by the curvature of space-time, and some of them that would have gone past the black hole end up falling in instead. This creates a region around the black hole called the photon sphere, where light rays orbit the black hole or get captured. And from our point of view, looking at the black hole from a distance, that capture region appears as an enlarged shadow, a dark circle bigger than the event horizon itself. The size of the shadow, about 50 microarc seconds, corresponds to a physical size of about 52 million kilometers at the distance of Sagittarius A star. That's consistent with a black hole of 4 million solar masses, just as expected from the orbital motions of the S stars. The image confirmed what decades of other observations had told us. Sagittarius A star is a supermassive black hole. There it is. You can see it. Or rather, you can see its absence, its shadow against the light. And the fact that it looks so similar to M87 star, despite M87 star being 1,000 times more massive and much more actively feeding, tells us something profound. General relativity predicts that all black holes, regardless of their mass, should look essentially the same when viewed from a similar perspective. The ring of light should have a size that's roughly 5 times the Schwarzschild radius, and the shadow should be centered in that ring. Mass scales everything up or down, but the proportions remain the same, and that's exactly what we see. M87 and Sagittarius A, vastly different in mass and activity, but producing nearly identical images when we photograph them at high enough resolution. It's a triumph of human ingenuity and persistence, of international collaboration, of the long, slow work of science. The monster at the center of our galaxy, invisible for all of human history, hiding behind veils of dust, detectable only through the motions of the stars around it and the faint glow of its radio and X-ray emission, finally seen. Not seen directly, because black holes by their nature cannot be seen, but seen in silhouette, their shadows cast against the background light of their own accretion disks. The image from the Event Horizon Telescope doesn't resolve every detail. It's not a photograph in the usual sense, not a sharp snapshot. It's a reconstruction from radio data, a composite of many observations, averaged and processed and carefully analyzed. But it's real. It's based on actual light, actual photons that traveled across 26,000 light-years of space and were captured by telescopes on Earth. We took a picture of the shadow of the monster at the heart of our galaxy, and it looks exactly like Einstein said it would. Magnetic fields and polarized light. The first image of Sagittarius, a star released in May 2022, showed us the black hole's shadow and the glowing ring of its accretion disk. But light carries more information than just brightness. Light has polarization, a property that describes the orientation of the electromagnetic waves as they propagate. And polarization can tell us about magnetic fields. When electrons spiral around magnetic field lines at speeds close to the speed of light, they emit what's called synchrotron radiation, and that radiation is naturally polarized in a direction perpendicular to the magnetic field. So if you can measure the polarization of light coming from a source, you can map out the structure of the magnetic field in that source. You can see, in a sense, the invisible scaffolding that organizes the plasma and guides its motion. In March 2024, the Event Horizon Telescope collaboration released a new analysis of Sagittarius A star, this time focusing on the polarization of the light from the accretion disk. And what they found was striking. The emission is strongly polarized, with some regions showing linear polarization as high as 40%. That's a lot. It means the magnetic field is well organized, not chaotic, at least in some parts of the accretion flow. The polarization pattern forms a kind of spiral around the black hole, with the polarization vectors swirling inward like water circling a drain. This tells us that the magnetic field is not just present, but dynamically important. It's strong enough and organized enough to shape the flow of the plasma, possibly even controlling how efficiently material can lose angular momentum and fall inward. Magnetic fields in accretion disks can do several things. They can generate turbulence through a process called the magneto-rotational instability, which helps transport angular momentum outward and allows material to spiral inward. They can also tap into the rotational energy of the black hole itself through a mechanism called the Blandford-Zinnerjec process, potentially powering jets of material that shoot outward perpendicular to the accretion disk. In very active black holes like M87 star, we see these jets clearly, enormous streams of plasma moving at nearly the speed of light, extending thousands of light years from the black hole Sagittarius. A star doesn't have obvious jets, at least not now. But the magnetic field structure suggests the basic machinery for launching them might be present. The polarization data also helps constrain models of the accretion flow. By comparing the observed polarization patterns to predictions from computer simulations, astronomers can test different ideas about what's happening near the black hole. Is the accretion disk thick or thin? Is it rotating in the same direction as the black hole's spin, or in the opposite direction? Is the magnetic field strong enough to be dynamically dominant, or is it just along for the ride? One intriguing puzzle that emerged from the polarization analysis is that some of the best fit models appear to suggest the accretion disk might be rotating in the opposite direction from what was previously inferred from other observations. This is surprising and not yet fully understood. It could mean that the disk is tilted or misaligned with respect to the black hole's spin axis, which would cause it to precess and show different rotation directions when viewed at different times, or it could indicate that the previous interpretations need revision, that there's something about the system astronomers don't fully grasp yet. The data is still being analyzed, and competing models are being tested against observations. This is the nature of frontier science. Every answer raises new questions. Every new observation constrains some models while leaving others open. The polarization data has given us a much more detailed picture of the magnetic environment around Sagittarius A star, but it's also revealed how much we still don't know. The monster's shadow is clear now, but the details of how it feeds, how its magnetic fields are generated and sustained, how its accretion disk is oriented and structured, these are questions that will require more observations, more simulations, more years of work. And more observations are coming. The Event Horizon Telescope collaboration is expanding, adding more telescopes to the array, improving sensitivity and resolution they're planning to observe at multiple wavelengths simultaneously, which will provide even more information about the physical conditions near the black hole, and they're working toward making not just images but movies, sequences of images that show how the accretion disk changes over time, how the bright spots move, how the flares evolve. Imagine seeing a movie of the shadow of Sagittarius A star, watching the glowing gas orbit the black hole in real time, seeing the effects of relativity play out in front of your eyes. That's the goal, and it's becoming technologically feasible. We're entering an era where we can study supermassive black holes not just as distant static objects, but as dynamic, evolving systems. We can watch them breathe in a sense, watch them flare and quiet, watch their accretion disks swirl and change, watch the interplay of gravity and magnetism and matter in the most extreme environments the universe has to offer. The magnetic fields around Sagittarius A star are strong, twisted and organized. They spiral inward with the accretion flow. They guide the motion of the plasma. They generate the radiation we see. They're part of the machinery that allows a black hole to feed, part of the complex physics that governs how matter behaves when gravity becomes overwhelming. And now, through the miracle of polarimetry and interferometry and patient analysis, we can see them. Not directly, but through their effects on light. We can map the invisible, measure the intangible, trace the magnetic architecture of the monster's lair. Tests of relativity. In 1915, Albert Einstein published his general theory of relativity, a radical reconception of gravity not as a force but as a consequence of the curvature of space-time itself. Massive objects, Einstein said, warp the fabric of space and time around them, and other objects move along the curved paths that result. What we perceive as the force of gravity is really just the geometry of space-time telling matter how to move. It was a beautiful theory, elegant and mathematically profound, and it made predictions that differed subtly from Newton's older theory of gravity. In most situations, those differences are tiny, almost negligible. For the motion of planets around the sun, for the fall of an apple from a tree, Newton's equations work perfectly well. But in strong gravitational fields, or when objects are moving at high speeds, relativity predicts effects that Newton's theory doesn't. One of the first tests of general relativity was the precession of Mercury's orbit. Astronomers had known for decades that Mercury's perihelion, the point in its orbit closest to the Sun, slowly advances. The orbit doesn't quite close. It creates a rosette pattern over many revolutions. Most of this precession could be explained by the gravitational influence of the other planets, by Jupiter and Venus and Earth all tugging on Mercury in complicated ways. But there was a residual precession, about 43 arc-seconds per century, that couldn't be accounted for with Newton's laws alone. Einstein's theory explained it perfectly. General relativity predicted exactly that amount of extra precession caused by the curvature of space-time near the Sun. It was a stunning success. One of the first pieces of evidence that Einstein's strange new theory was actually correct. But Mercury's orbit, close as it is to the Sun, is still in a relatively weak gravitational field. The curvature of space-time near the Sun is measurable, but it's not extreme. To really test general relativity, to see if it holds up in the most intense gravitational environments, you need something much more extreme than the Sun. You need a supermassive black hole. Sagittarius A star provides exactly that testing ground. The stars orbiting close to it, particularly S2, experience gravitational fields millions of times stronger than anything in our solar system, and they move fast enough that relativistic effects become significant. This makes them perfect probes of general relativity in an extreme regime. We've already talked about Schwarzschild precession, the advance of the perihelion of S2's orbit. That's one test, and Einstein passes with flying colors. But there are others. One is gravitational redshift. According to general relativity, time runs slower in strong gravitational fields. If you're deep in a gravity well, your clock ticks more slowly than a clock farther away. This effect is called time dilation, and it has a consequence for light. Light emitted from deep in a gravity well loses energy as it climbs out, and lower energy light has a longer wavelength, which for visible light means a shift toward the red end of the spectrum, hence gravitational redshift. For S2, at its closest approach to Sagittarius A star, general relativity predicts a specific gravitational redshift in the light from the star. The star's spectral lines, the characteristic wavelengths at which it absorbs or emits light, should be shifted to longer wavelengths by a calculable amount depending on how deep in the black hole's gravity well the star is at any given moment. Astronomers measured this redshift during S2's perihelion passage in May 2018. They watched the star swoop past the black hole, and they measured the wavelength of its light with high precision, and what they found matched Einstein's predictions exactly. The observed redshift agreed with general relativity to within the measurement uncertainties. If there were deviations from Einstein's theory, they were too small to detect. This was another triumph. The 2020 Nobel Prize to Reinhard Genzel and Andrea Ghez recognized not just the discovery of the black hole, but the precision of their measurements, which allowed these tests of general relativity to be performed for decades of work tracking S2 and the other S stars, for building the instruments and developing the techniques to measure stellar positions and velocities to extraordinary accuracy, for using those measurements to weigh a black hole and test the fundamental theory of gravity in its most extreme regime. They were honored. But the tests continue. Every orbit of S2 provides more data, more opportunities to check whether general relativity still holds. And there are other effects to measure. One is frame dragging, or the lens-thirring effect, where a rotating massive object drags spacetime around with it. If Sagittarius A star is spinning, and it probably is, then the space-time immediately around it is rotating too, like water swirling around a spinning ball. This rotation should affect the orbits of nearby stars in subtle ways, causing their orbital planes to precess. Measuring frame dragging around Sagittarius A star is difficult because the effect is small and there are other things that can cause orbital precession, but with enough precision and enough time, it should be possible. Astronomers are working on it, refining their measurements, extending the baseline of observations, waiting for the signatures of frame dragging to emerge from the noise. Another test involves the black hole's shadow. The size of the shadow in the Event Horizon Telescope image depends on the black hole's mass and spin. A faster spinning black hole has a smaller shadow, because the rotation allows material to orbit closer to the event horizon before it has to plunge in. By measuring the shadow size precisely and comparing it to the mass determined from stellar orbits, astronomers can potentially determine the black hole's spin. This work is ongoing. The current images aren't quite sharp enough to measure the shadow size to the needed precision, but future observations with an expanded Event Horizon Telescope might be. And then there are the flares, the sudden brightenings in X-rays and infrared that appear to come from material very close to the event horizon. Some theoretical models propose that these flares might be hotspots in the accretion disk that orbit the black hole several times before dissipating or falling in. If this interpretation proves correct, then by tracking the motion of these hotspots, astronomers could potentially map out the trajectories of matter in the innermost regions where relativistic effects are most extreme. They could observe, in real time, matter moving along geodesics, the curved paths through space-time that general relativity predicts. Every test so far has confirmed Einstein's theory. Every measurement of orbital precession, every detection of gravitational redshift, every image of the black hole's shadow, every observation of how light bends around the massive center, all of it agrees with general relativity. There are no signs of breakdown, no hints that we need a new theory of gravity, at least not yet. In the century since Einstein formulated his equations, they've passed every test we've thrown at them, even in the most extreme environments we can observe. This is both reassuring and, in a way, disappointing. Reassuring because it means we understand gravity, at least in the classical regime where quantum effects can be ignored. Disappointing because physicists love to find places where theories break down, where new physics emerges. A deviation from general relativity would be exciting. It would point the way toward a deeper theory, perhaps toward the quantum theory of gravity that physicists have been seeking for decades. But so far, Einstein endures. The monster at the center of our galaxy dances to the tune he wrote, and the stars around it follow the paths his equations predict. It's a testament to the power of human thought, to the possibility of understanding the universe through mathematics and observation. A man sitting in a patent office in Switzerland, doing thought experiments about falling elevators and beams of light, worked out the nature of gravity. And a century later, we test his ideas using supermassive black holes millions of times the mass of the Sun, and they still hold true. That's extraordinary. That's beautiful. That's science at its best. Living near a monster, A reflection. What would it be like to live near Sagittarius A star? Not at a safe distance of 26,000 light-years, where we are insulated from its power by sheer distance and the empty dark of interstellar space, but close, orbiting within light days or light hours of the event horizon, feeling the full weight of its gravitational pull, experiencing the most extreme physics the universe has to offer without falling in. It would be violent. The environment near a supermassive black hole is one of extremes, of powerful forces and relentless radiation. The accretion disk, thin as it is a maelstrom of superheated plasma, moving at substantial fractions of the speed of light. Magnetic fields thread through it, strong enough to guide the flow of matter and occasionally snap in magnetic reconnection events that release tremendous bursts of energy. If you could somehow exist on a planet orbiting close to Sagittarius A star, if you could somehow survive the radiation and the tidal forces and all the other hazards, you would see strange skies. The black hole itself would dominate the view, a vast circle of darkness surrounded by a glowing ring. But the darkness wouldn't be absolute, because gravitational lensing would bend the light from stars and gas behind the black hole around it, creating a distorted funhouse mirror view of the universe. You might see multiple images of the same stars, bent around the black hole's curvature, appearing in places where they shouldn't be. Stars directly behind the black hole would appear as a ring around its shadow, their light bent by 180 degrees by the extreme curvature of space-time. And the colors would be wrong, shifted by the Doppler effect and by gravitational redshift. Light climbing out of the black hole's gravity loses energy, becomes redder, while light falling in gains energy, becomes bluer. The accretion disk spinning at a substantial fraction of light speed would be brighter and bluer on the side rotating towards you, dimmer and redder on the side rotating away. This is called relativistic beaming, and it creates an asymmetry in the brightness of the disk that depends on the viewing angle and the rotation direction. The sky would be bright with X-rays and gamma rays, invisible to human eyes but deadly to unprotected tissue. The accretion disk glows across the entire electromagnetic spectrum, from long radio waves to hard X-rays, with peak emission in the ultraviolet and X-ray bands where the plasma is hottest. If you had X-ray vision, if you could see those high-energy photons, the black hole would be blazing, a beacon of radiation pouring out energy as gas spirals inward and heats to billions of degrees. And time would flow differently for you. This is one of the most profound and strange predictions of general relativity. Time dilation in gravitational fields. The stronger the gravity, the slower time runs. If you were orbiting close to Sagittarius A star, experiencing intense gravitational acceleration, your clock would tick more slowly than clocks farther away. This isn't an illusion or a trick of measurement. It's a real physical effect. Time itself, the rate at which processes unfold, the rhythm of causality, the fundamental flow of duration, would be different for you than for someone far from the black hole. Imagine it. If you could spend a year orbiting at a few hundred Schwarzschild radii from the event horizon, depending on your exact distance and orbital velocity, when you return to the outer regions, you might find that more time had passed there than you experienced. Your friends could have aged while you remained relatively younger, not only because of motion at high speed as special relativity describes, but because the gravitational field you were immersed in altered the flow of time itself. The exact amount of time dilation would depend on your distance from the black hole and your orbital parameters, but the effect would be real and measurable. This effect is real and measurable even in the gravitational field of Earth, which is extraordinarily weak compared to a black hole. Atomic clocks at sea level tick slightly slower than identical clocks at high-altitude GPS satellites have to correct for both special and general relativistic time dilation to maintain accurate positioning. Near Sagittarius A star, the effect would be dramatic, unavoidable, life-altering. The radiation would be a concern too. The accretion disk emits X-rays and ultraviolet light from its superheated gas. The magnetic flares can accelerate particles to enormous energies, creating bursts of gamma rays. If you were close enough, this radiation would be lethal without extraordinary shielding. The S-stars survive because they're stars, massive balls of plasma held together by their own gravity. But a planet, a spacecraft, a living organism would be in constant danger from the intense radiation environment. And yet, the stars do survive. S2 swoops past at 120 astronomical units, moving at 9,000 kilometers per second, and it remains intact. It doesn't get torn apart by tidal forces, doesn't evaporate under the radiation bombardment, doesn't spiral inward and cross the event horizon. It persists. It endures. Every 16 years it makes the same terrifying plunge and emerges safely on the other side. There's something almost poetic about that resilience. These stars exist in an environment that seems like it should destroy them, and yet they dance on, orbit after orbit, following the gravitational choreography that Einstein described. They're stable. Their orbits, though extreme, appear to be long-lived. Based on the dynamics of the system, S2 has likely been orbiting Sagittarius A star for millions of years, and barring any unexpected perturbations, it could continue for millions more, as long as nothing disrupts it enough to send it into the black hole or fling it out into the galaxy. What does that tell us? Perhaps it tells us that even in the most extreme places there's order, there's predictability. The universe doesn't become arbitrary and chaotic just because the forces are strong. In fact, in some ways, extreme environments are simpler than moderate ones. Near Sagittarius, a star, there are no complications from other stars' gravity, no three-body interactions, no slow perturbations that might destabilize orbits over eons. There's just the black hole, massive and dominant, and the stars that orbit it, following the precise paths that relativity demands. It also tells us something about what it means to exist, to persist, in the face of overwhelming forces. S2 doesn't fight the black hole's gravity. It doesn't resist. It falls, and in falling it moves sideways fast enough that it never quite hits the center. It surrenders to the geometry of space-time and finds stability in that surrender. There's a lesson there, perhaps, not a literal one about how to live your life, but a metaphorical one about the relationship between structure and surrender, between order and extremity. If you were living near Sagittarius A star, you would be living at the edge of what's possible. Not quite at the event horizon, not quite in the regime where nothing can escape, but close enough to feel the monster's breath, so to speak. Close enough that general relativity isn't just a theoretical curiosity, but the fundamental fact of your existence. Every moment would be a testament to the curvature of space-time, to the reality that mass warps the fabric of the universe, that gravity is geometry. And maybe, in a way, we do live near a monster. It's far from us, yes, 26,000 light-years, but it's there. It's the gravitational anchor of our galaxy, our Sun, and therefore our Earth, and therefore all of us orbit Sagittarius A star. Our orbital period is about 230 million years, which is slow, sedate, nothing like the screaming 16-year orbits of the S stars, but we're orbiting nonetheless. The monster shapes our trajectory. It holds the galaxy together. It's part of the architecture of our cosmic home. We're not in danger from it, not at our distance. We'll never fall in. Astronomers predict that the Milky Way and Andromeda galaxies are on a collision course and will likely merge in several billion years, and when that happens, the two supermassive black holes at their centers would eventually spiral together and merge, creating an even more massive black hole. But by that time, our Sun will likely have evolved into a red giant, and the Earth as we know it will be uninhabitable anyway, so it's not something we need to worry about. For now, for the lifetime of our species and countless generations to come, we orbit safely, far from the center, coasting through the outer reaches of the disk. But knowing it's there, knowing what it is and how it works, adds a dimension to our understanding of our place in the cosmos. We live in a galaxy with a supermassive black hole at its heart. That's our reality. That's part of the story of where we come from and where we are. And there's something both humbling and thrilling about that knowledge. The future of discovery. The story of Sagittarius. A star is far from over. Every discovery we've discussed, every image and measurement and orbital trace is a chapter in an ongoing investigation. The monster is still there, still feeding, still warping space-time, still waiting for us to learn more about it, and we will. The tools are getting better, the questions are getting sharper. The future of studying the Milky Way's supermassive black hole is bright with possibility. The Event Horizon Telescope is expanding. When the collaboration released the first image of Sagittarius A star in 2022, they were using 8 radio telescopes. Now there are plans to add more, increasing the number of baselines, the number of pairs of telescopes whose data can be combined. More baselines mean better image reconstruction, sharper resolution, the ability to see finer details in the structure of the accretion disk, and the shadow future observations might reveal asymmetries in the shadow itself, features that could tell us about the black hole's spin and the orientation of its rotation axis, and they're planning to observe at multiple wavelengths. The first images were made at a wavelength of 1.3 millimeters, but Sagittarius A emits across a broad range of the spectrum, from radio waves to X-rays. By observing at different wavelengths simultaneously, astronomers can probe different physical processes, different regions of the accretion flow. Lower frequency radio waves come from farther out, where the gas is cooler and less dense. Higher frequencies and shorter wavelengths, like infrared and X-rays, come from closer in, where the gas is hotter and denser. Combining multi-wavelength observations will give a much more complete picture of the black hole's environment. There's also the possibility of making movies, not just static images, but sequences that show how the accretion disk changes over time. The gas orbits the black hole in minutes, so if you observe continuously for hours or days, you should be able to see features move, watch bright spots circle the black hole, track the evolution of flares. This requires enormous amounts of data and sophisticated analysis, but it's technically feasible. And the scientific payoff would be enormous. You could test models of accretion flows by seeing if they predict the right timescales and patterns of variability. You could watch general relativistic effects play out in real time, as light from orbiting gas gets beamed and blue-shifted and red-shifted by its motion. NASA's James Webb Space Telescope is also contributing. Webb observed Sagittarius A star in infrared light, watching the flares with unprecedented time resolution. These observations, combined with simultaneous X-ray observations from other telescopes, are helping to constrain models of what causes the flares. Is it magnetic reconnection, as most astronomers think, or something else? And what do the flares tell us about the magnetic field structure and the accretion rate? There are also plans for X-ray polarimetry missions that could measure the polarization of X-rays from Sagittarius A star. X-ray polarization is sensitive to the geometry and magnetic field structure very close to the black hole, even closer than the radio emission that the Event Horizon Telescope sees. This could provide yet another window into the innermost regions of the accretion flow. And then there are the stars. Astronomers are still tracking S2 and the other S stars, still refining measurements of their orbits, still looking for additional relativistic effects. With each orbit of S2, the data gets better, the uncertainties shrink, the patterns become clearer. With each perihelion passage, there's another opportunity to measure gravitational redshift and Schwarzschild precession to higher precision, to test general relativity in ever more stringent ways. Over time, subtle effects like frame dragging might become detectable. Frame dragging, or the lens-thirring effect, is where a rotating massive object literally drags space-time around with it, creating a kind of gravitational whirlpool. If Sagittarius A star is spinning rapidly, and most supermassive black holes probably are, then the region of space-time immediately around it should be rotating too, pulled along by the black hole's angular momentum. This should cause the orbital planes of nearby stars to precess slowly, shifting their orientation over time in a way that depends on the black hole's spin rate and direction. Detecting frame dragging is extraordinarily difficult. The effect is small, easily masked by other perturbations. But with decades of precise measurements, with careful modeling of all the other effects that could mimic frame dragging, it might eventually be possible to tease out the signal from the noise. And if we can measure frame dragging, we'll learn about the black hole's spin, which in turn tells us about its history, about how it formed and how it's grown over billions of years. There's also the search for more stars, particularly stars in even more extreme orbits. S4714 holds the current record for closest approach, but there might be others we haven't found yet. There might be stars that pass even closer, that experience even stronger. Gravitational fields that could provide even better tests of general relativity. Finding them requires patient observation and careful analysis of crowded star fields, but it's entirely possible that more extreme S-stars are out there waiting to be discovered. and astronomers are looking for other objects near Sagittarius A star too. Are there intermediate mass black holes orbiting nearby? These would be black holes with masses between stellar mass black holes and supermassive ones, perhaps a few hundred or a few thousand times the mass of the Sun. If they exist near Sagittarius, a star, they could have been captured by the supermassive black hole's gravity, and they'd betray their presence through their gravitational influence on nearby stars. Finding intermediate mass black holes would help explain how supermassive black holes form and grow, providing clues to the early history of the galaxy. There's also the question of the black hole's spin. We don't know yet how fast Sagittarius A star is rotating. Is it spinning rapidly, close to the maximum rate allowed by general relativity? Or is it spinning slowly, perhaps because it accreted material from different directions over its history, and the angular momentum averaged out? The spin affects the structure of space-time around the black hole, affects the size and shape of the shadow, affects how efficiently the black hole can convert accretion energy into radiation or jets. Measuring the spin is a major goal for future observations. And then there's the broader question of how Sagittarius A star fits into the story of our galaxy. How did it form? How has it grown over billions of years? How has it interacted with the surrounding galaxy, influencing star formation and gas flows? Supermassive black holes and their host galaxies co-evolve, each shaping the other over cosmic time. Understanding that relationship, understanding how black holes like Sagittarius A star affect the galaxies they live in, is one of the big questions in modern astrophysics. The future is full of questions, and that's exciting. Every answered question reveals new puzzles, new avenues to explore. We've come so far in understanding Sagittarius A star, from the first radio observations in the 70s to the first image in 2022, but we're still just beginning. The monster at the center of our galaxy still holds secrets, still challenges us with its extreme physics and its complexity. But we're watching, we're measuring, we're building better instruments and developing better theories. We're patient and we're persistent, and slowly, piece by piece, observation by observation, we're learning, we're pulling back the veil, illuminating the darkness, understanding the monster, and in doing so, we're understanding ourselves, our place in this galaxy, our relationship to the massive heart around which we orbit. The work continues, the discoveries will keep coming, and we get to watch, to learn, to marvel at what we find. There's a quiet joy in that, a deep satisfaction in the pursuit of knowledge for its own sake. We'll never visit Sagittarius A star, never approach closer than our current safe distance of 26,000 light years. But we can see it now, can measure it, can understand it. And that's enough. That's more than enough. That's everything. Conclusion. We've journeyed a long way tonight, you and I. From the comfort of the familiar, from the Earth and the Sun and the planets we know, out to the center of the Milky Way. We've met the monster that lives there, not a creature of mythology, but a physical object, a supermassive black hole about 4.3 million times the mass of our Sun, sitting in darkness at the gravitational heart of our galaxy. We've seen how it was discovered, not through direct observation, but through the patient watching of the stars that dance around it, Stars like S2 that orbit at 3% of the speed of light, carving rosette paths through space-time that perfectly match Einstein's predictions. We've learned about its size, small for something so massive, an event horizon 12 million kilometers across, hidden behind dust and distance. We've explored why it's so quiet, barely feeding, barely glowing, a sleeping giant that last ate well 5 million years ago. We've watched as astronomers built a virtual telescope the size of Earth, and after 5 years of painstaking work, captured the first image of its shadow, a dark circle against a ring of glowing gas, proof that what theory predicted and stellar orbits implied is really there. We've seen the magnetic fields that spiral around it, strong and organized, shaping the flow of plasma. And we've understood how Sagittarius A serves as a laboratory for testing general relativity in its most extreme form, how every measurement confirms Einstein's century-old insights into the nature of space-time and gravity. And we've reflected on what it might be like to exist near such an object, to feel the full force of its gravitational pull, to experience time dilation and extreme radiation, and the strange beauty of a universe bent and warped by mass. It would be terrifying and magnificent, hostile and ordered, a place where physics becomes pure and elemental. But perhaps the most important thing to take away from this journey is simply the fact that we can make it at all. That we, small creatures on a small planet, orbiting an average star in the outer reaches of a spiral galaxy, can nevertheless peer across 26,000 light-years of space and see, truly see, the monster at the center. That we can measure its mass, trace its gravitational influence, capture its shadow, test the fundamental laws of physics against its extreme reality. That's astonishing. That's a testament to human curiosity and ingenuity and the power of science to reveal truths about the universe that are far beyond the reach of our senses alone. Sagittarius. A star is still there, right now as you listen to these words. It's still warping space-time, still pulling on the stars around it, still glowing faintly in radio and X-ray light. It's been there for billions of years and will remain for billions more. Long after the Earth is gone, long after the Sun has died. It's permanent in a way that almost nothing else is, a fundamental part of the architecture of the galaxy, the massive anchor that keeps everything in its place. And we orbit it. Not quickly, not dramatically, but we orbit it nonetheless. Our Sun makes one slow circuit every 230 million years, and we're carried along for the ride. The monster at the center shapes our trajectory, shapes the galaxy we live in, shapes the distribution of stars and gas and dark matter that defines the Milky Way. We're part of its story, even if we're very far from its immediate influence. There's something deeply calming about that perspective, about understanding our place in the larger cosmic structure. We're not at the center, and that's fine. We're out here on the edge, in a quiet neighborhood where stars live long lives and planets can form and life can emerge and evolve. The center is too violent, too extreme, too dangerous for something as delicate as life. But from our safe vantage point, we can still study it, still understand it, still appreciate the role it plays in the galactic ecology. So let's be grateful. Grateful for the astronomers who spent decades watching S2 crawl across the sky. measuring its position with extraordinary precision, waiting patiently for the data to accumulate. Grateful for the engineers who built the Event Horizon Telescope, who figured out how to synchronize observations across the entire planet, who transported hard drives full of data from the South Pole and Chile and Hawaii and Spain. Grateful for Einstein, who gave us the mathematical framework to understand black holes even though he died before we had evidence they actually existed. Grateful for our position in a galaxy with a relatively quiet, supermassive black hole, in an era when we have the technology to study it. And grateful perhaps just to live in a universe that is knowable, that follows laws we can discover, that rewards curiosity with understanding. The monster at the center of our galaxy isn't a mystery anymore, not really. It's a supermassive black hole, and we know its mass and its size and its behavior. There are still things to learn, still questions to answer, but the fundamental nature of the object is clear. We've pulled back the veil, we've seen the invisible, we've understood the monster. And understanding in the end is what science offers us. Not certainty, not absolute truth, but the steady accumulation of knowledge, the gradual clarification of what's really out there beyond our immediate experience. The universe is strange and vast and often counterintuitive. Black holes exist, space-time is curved, time runs at different rates in different places, light bends around massive objects. These are strange ideas, far removed from everyday experience, but they're true. The universe works this way, and we've figured it out. So rest now. Let these ideas settle in. Let the image of Sagittarius A, star, that dark shadow against glowing light, linger in your mind. Let the thought of S2's screaming orbit around the black hole fill you with wonder. Let the knowledge that all of this is real, that these objects exist out there in the dark, that we've seen them and measured them and understood them, bring you a sense of deep satisfaction. The monster at the center is there, quiet and massive, shaping the galaxy with its gravity. And we're here, watching and learning and marveling. That's a beautiful thing. That's enough. If this journey through the cosmos resonated with you, if you found wonder in the hidden heart of our galaxy, please consider liking this video and subscribing to the channel. Your support helps these explorations reach others who might be searching for the same sense of cosmic perspective, the same quiet joy in understanding. Share your thoughts in the comments if you feel moved to do so. And if you'd like to explore more mysteries of the universe, more journeys to the edge of what we know, there are other videos waiting for you. But for now, just rest. Let your breathing slow. Let your mind drift peacefully. You've traveled far tonight, all the way to the center of the galaxy and back. You've met a monster made of pure gravity, seen stars dance at the edge of the impossible, watched light bend around darkness itself, and you've returned safely, carrying with you a deeper understanding of the cosmos we inhabit. Thank you for joining me on this voyage. Thank you for your curiosity, your patience, your willingness to peer into the dark and see what's really there. The universe is vast and strange and beautiful, and it's a privilege to explore it together. Good night, and thank you for journeying with me to the monster at the center of our galaxy, to the quiet heart of the Milky Way, to the place where more than 4 million suns worth of mass warps the universe into something profound and beautiful. Rest well. Dream deeply. And remember that even in the darkest places, even at the center of a black hole's shadow, there is order, there is beauty, and there is light.